How's it going today, guys? So I figured it'd be a good time to go over the current sensing circuit. I made a video a long time ago that had the current sensing circuit in there. Didn't have any sort of explanation. I'm kind of going through those videos and adding explanations, and I'm going to work on making some more videos for everybody. I mainly focus on FPGAs and microcontrollers, but I think I'll probably move into simple circuits and stuff like that just to give a good roundabout approach to these things for anybody to view online. So, of course, this circuit was ultimately hooked up to an FPGA, but there's nothing really FPGA related in this video. So the circuit you see in front of you on the screen is the current sensing circuit that I built for a project in school. And it was basically there was an H bridge running motors, and there was some sense resistors across these motors to see if there was any sort of overvolt. So you can measure these sense resistors and tell the motors to shut off, or tell the control for the motors to shut off, or even the power to the motors to shut off. So this circuit is just to tell the control board that there has been an overcurrent, and to tell the control board to stop driving the motors for a moment. Now there is a little bit of logic that goes into that. If you guys are interested in the logic that I used for that inside the FPGA, I can post that. And I might just put a GitHub link to the driver that I used, the FPGA code that I used, but it's pretty simple logic, right? So essentially, there's current running through a motor, and then that goes across a very low resistance resistor, and that current creates a voltage drop across one of these lines. For one motor, it's this line. For the other motor, it's this line. That voltage measurement is then run into this comparator, and it's compared to whatever voltage is on this line. If we kind of work backwards from the circuit, we look at this Opto Coupler, which is basically an LED driving a transistor for these purposes, right? So this line is held up to 14 volts, and this is continually showing a 1, right? So this is continually shining light on this transistor. Well, if we take this line here and we drag this line to ground, then it's going to make it's going to be a 0 here. There won't be any current moving through this branch, and this resistor won't read anything, and nothing will come through on this side, right? So essentially this compares this voltage to this voltage. If this voltage is higher than this voltage, then you will get it'll leave this open, right? And if this is open, then this voltage will make a current across this resistor, and this resistor basically just limits the current that goes through this LED. And then open, that means it's shining, the LED is shining, and it's turning on this phototransistor. Right? So this phototransistor is able to turn on. It allows a connection to ground. You get 3.3 volts through a 20K ohm resistor. Now on this side, if this is tied to ground, then data is going to be 0, right? But if it's not tied to ground, then you get no current running through this resistor. And with no current running through this resistor, that means it doesn't take a voltage drop. If it doesn't take a voltage drop, then 3.3 volts is here. So if this transistor here is on, this data line says 0. If this transistor here is off, this data line says 3.3. So we kind of reversed the logic from here to here. So basically you've got the sense, let's start from the beginning. The sense resistor, if that voltage is higher than this voltage, you'll have an open, which allows the current to run through this diode, which means you're going to be in this state. That means that we're overcurrent. So if we're overcurrent, then this will be on. And if this is on, then this will be on. And if this is on, this will be down, which will be 0. So this basically says if current is greater than it should be, put a 0 here. If current is less than it should be, in the case that this is smaller than this, This voltage is smaller than this. It will connect this to ground. If this is connected to ground on any point in this line, then this will get pulled to 0 and you won't have any light come out here. If this is 0, this is off, and if this is off, this is going to be pulled up to 3.3 volts. So in the case of over voltage, you'll have a 0. In the case of regular, normal running or operating voltage, you'll have a 1. So it's very important that the op-amp or the comparator found in the circuit is an open collector comparator. This is the schematic for the LM393. It's simplified, obviously. And we don't really, for this discussion, we don't really care about all of this circuit here. What's important here is this last output piece, right? So this is, it's basically just a BJT, and you can turn the thing on or off by putting current into it, right? So when it's off, this output is open, right? So it's an open collector comparator. When this turns on, it connects this output directly to the ground. That allows this circuit to be pulled all the way to the ground rail, which is important for the circuit that we're doing here, because as you see, we're basically pulling this line to ground, which is going to put a little current through here, but not much at 20 k ohm, right? And that will make this 0, meaning no current will go through this LED here. Now, when it's not pulled to ground, when it's open collector, right, this will be open, which means this line will be pulled up to this voltage here. And this is sized so that there's enough current to turn on the LED at 14 volts. If you have any questions, leave those down below. If you have any comments, leave those down below. I always miss things. I always mess things up. Please correct me if I'm wrong somewhere. There's no issues here with that. We're all learning always. Usually I use Google to verify myself a lot of times throughout the, just because there's just so much always going on. You gotta make sure everything's right. So anyways, y'all have a good day and love what?